Hess's law of constant heat summation. Hess's law of constant heat summation. It's a very, very important topic, and at least one question is generally asked on this topic. So this particular topic simply says that suppose I convert carbon to carbon dioxide in one single step, for which, say, enthalpy change for the reaction is delta H, let us say. And there is another way of converting carbon to carbon dioxide. At first, it will be burning in insufficient supply of oxygen, producing carbon monoxide. So the enthalpy change is delta H1. And then the carbon monoxide further combines with oxygen to give carbon dioxide. So let us say that the enthalpy change during this particular process is delta H2. So the Hess's law says that it doesn't matter in how many steps the carbon is getting converted to carbon dioxide. Here also the carbon is getting converted to carbon dioxide in a single step, and here it is getting converted to carbon dioxide in two steps. So according to Hess's law, the enthalpy change, the total enthalpy change, during transformation of any substance remains the same whether the transformation takes place in one step or more than one step. Okay, now we have learned in the first class of thermodynamics about a particular topic called state function. And what are state functions? The state functions depend only upon initial and final states, but not upon how the final state is achieved or what is the path taken. So delta H is a state function. So it does not depend upon in how many steps the conversion is taking place. If the initial state and final state are same, the enthalpy change will remain the same. Is it understood now?
Yes, sir.
Yes, sir.
Okay. So this is what is the Hess's law all about. And you can say that it is a further extension of first law of thermodynamics as well, according to which the sum total of energy remains the constant. Energy can neither be created nor be destroyed. So whether the carbon is getting converted to carbon dioxide in a single step or more than one steps, what will remain same is the enthalpy change. Complete this, then we will try to do the sums on Hess's law. Oh yeah, can I proceed?
Yes, sir.
Okay, fine. So let us try out a question on Hess's law. I hope I get some example on it. Okay, write down. The enthalpy of combustion of benzene the enthalpy of combustion of benzene is minus 3267 kilojoules per mole. Calculate the enthalpy of formation of benzene if the enthalpies of formation of CO2 and H2O are minus 393.5 kilojoules and minus 285.83 kilojoules per mole respectively. Per mole respectively. Okay, so first you write down the question with proper values, whatever has been provided. The enthalpy of combustion of benzene is minus 3267 kilojoules per mole. Calculate the enthalpy of formation of benzene if enthalpies of formation of CO2 and H2O are minus 393.5 kilojoules and minus 285.83 kilojoules. Written?
Yes,
Can I
sir.
proceed? Okay. So at first, we need to see that what needs to be calculated. So in this solution, what we need to find is enthalpy of combustion of benzene is given, enthalpies of formation of carbon dioxide and water are given, and you need to calculate the enthalpy of formation of benzene. So what is the equation for enthalpy of formation of benzene? Last class we have discussed that anything when it is formed, okay, it should be formed from the constituent elements. What are the elements which are responsible in formation of benzene? It
Carbon
is
and
carbon
Carbon
hydrogen.
and hydrogen.
and hydrogen. So if we balance it, So for this reaction, delta H needs to be calculated. Okay. Now, what are the things given? You are given combustion of benzene. So benzene is combusted, means benzene is not solid, sorry, it is liquid. So benzene upon combustion gives carbon dioxide and water because it's a hydrocarbon. So don't forget to balance any reaction. 6 carbon dioxide, 3 H2O, 2 6 are 12 plus 3 15, so 15 by 2O2. So in front of it we write the value provided. Combustion of benzene is given to be minus 3267 kilojoules. Formation of carbon dioxide. So carbon solid plus oxygen gas gives carbon dioxide. So delta H for this process is minus 393.5 kilojoules. Further, formation of water is given. So hydrogen gas plus half O2 gas gives water. Delta H is provided to be minus 285.83. So let this equation be equation 2, this be equation 3. So far we have not done anything. What we have only done is I have written every information in terms of equation. So with the help of equation 1, 2 and 3, we need to find out the delta H value of the required equation. Write this much first and don't miss out any point. As I said, it's an important topic. So tell me after you have completed.
Sir, in 2 fine, it should be 6C, na?
6C, yes. 6 carbon. Make it 6 carbon. Thank you, Trisha.
Thank you, sir.
Anyone having any confusion, please clear it out. I hope it is understood.
Sir, in equations 2 and 3, del H will be del H 1 and 2.
No. All we will be considering as delta H.
Okay, sir.
Okay, so delta H for the respective reactions. But I have specified the reaction numbers as 1, 2, 3. Okay, now the main aim. Have you all written down all the 4 reactions?
Yes, sir.
Yes,
Okay.
sir.
So with the help of the 3 reactions, we need to calculate the delta H of the first reaction. So the first reaction has 6 moles of carbon, 3 moles of hydrogen, and 1 mole of benzene, and that too on the right hand side. But according to the given equation, benzene is present in which side?
Right hand side.
No, this is not right hand side. According to the equation 1, where is benzene?
Oh, left hand side.
Left
Left
hand
side.
side. But actually, where is benzene required according to the demand of the situation?
Right hand side.
Right hand side.
So for that, we need to reverse equation 1. Okay. Reversing equation 1. So when we reverse any equation, last class, did we discuss that delta H will become just the opposite sign?
Yes, sir.
Okay. So since in the required equation C6H6 is on the right hand side, and here the C6H6 is on the left hand side, so I have to convert all of them according to this. So for that, the first reaction, the first equation must be reversed. Clear?
Yes, sir.
Plus. Now come to carbon. Where is the carbon? In which equation carbon is present?
2.
Equation 2.
2.
But how many moles of carbon are actually required according to the demand of the situation? 6 moles.
6.
But here it is 1 mole, isn't it? So all through this reaction is to be multiplied with 6. So 6 into equation 2 plus hydrogen, how many moles?
3.
6.
3. And in the third equation, hydrogen is 1 mole. So we will have to multiply 3 into equation 3. Understood?
Yes, sir.
Yes, sir.
So as there are 3 components, I have to make changes in these equations whose values are given accordingly. This was 1 mole, fine, but on the right hand side, so I need to reverse equation 1. So when I reverse equation 1, the equation will become 6 carbon dioxide gas plus 3 H2O liquid gives C6H6 liquid plus 15 by 2 O2. Isn't it?
Yes, sir.
So along with it, you also write down the changed value of delta H. Now it is plus 3267 kilojoules. Okay. So this is reverse of equation 1 plus 6 into equation 2. The second equation is to be multiplied all through with so last class we discussed that if you multiply any number with the whole equation, you have to multiply the same number with the delta H value as well, isn't it?
Yes, sir.
Yes, sir.
Plus 3 into equation 3 add them up, and upon addition you are supposed to get this required equation. If you get this required equation, then the respective delta H value will be the answer. So some components will get cancelled. 3H2O, 3H2O will get cancelled. What else can we cancel off?
6 O2, 3 by 2 O2, and 15 by 2 O2.
So 6 plus 3 by 2 O2 is how much?
15 by 2.
15 by 2 O2. So when you add them up, it will be 15 by 2 O2, and this and this will get cancelled. So ultimately what is remaining is 6 carbon plus 3H2 gives C6H6. So do we get what we required or not?
Yes, sir.
Yes.
So accordingly, you add up these three values and tell me what is the answer coming out. So addition of these three equations give us the required solution. So accordingly, the respective delta H also needs to be added up after making changes. So do the calculation and tell me how much is the delta H coming out. Plus
Sir, I got
3267,
50.51.
50 point,
50.51.
50.51. Just see what others are getting. The answer given is
Sir, 48.6.
48.51. Just see whether you are getting this answer or not. This is what is given in the book.
Yes, sir.
Yes, sir, made a mistake.
Is it clear? How did we do the reaction? Do the Hess's law application?
Oh, sir.
Akash, is it clear?
Yes, sir.
Okay. Now, same question has an alternate solution. Okay, so let me show that alternate solution also. What is the alternate solution? So the equation that is required was enthalpy of combustion of benzene. So benzene C6H6 liquid plus 15 by 2 O2 gas gives 6 CO2 gas plus 3 H2O liquid. And you need to calculate delta H for this. Formation of products minus enthalpy change of formation of reactants. So what are the products? Carbon dioxide and water are the products. So we are going to write delta FH of carbon dioxide multiplied with 6 plus delta FH of water multiplied with 3. So these are the products. We need to sum them up. Minus. Reactants are benzene, and oxygen. See whether this expression is clear to all of you or not. Six into enthalpy of formation of carbon dioxide plus 3 into enthalpy of formation of water minus enthalpy of formation of benzene plus 15 by 2 into enthalpy of formation of oxygen. Clear?
Yes, sir.
Now you put in the values. What is the enthalpy of formation of carbon dioxide given? Minus
Minus 393.5.
0.5 plus what is the enthalpy of formation of water given?
Minus 285.83.
83 minus this much is given to be how much?
Minus 3267.
Minus 3267 plus this is not given. Why? Because it is already present in free elemental state. Enthalpy of formation of any element, okay, is always 0. Why? Because it is already present in the elemental form, and anything that is formed has to be from the element. Now element to element there is no energy required. So for pure elements the enthalpy of formation will always considered to be 0. So will it not come out to be same expression? Understood?
Yes, sir.
So both ways you can proceed, but what you need to understand is in order to proceed in this way, all enthalpies of formation should only be given. But instead of enthalpy of formation, if some other enthalpies are given, so prefer the Hess's law. This method will not be preferable. But here, because all are enthalpies of formation which are given, and from that we need to calculate the enthalpy of combustion, so I can solve it by any of the two methods. Clear?
Okay, sir.
Oh, sir.
Understood?
Oh, sir.
Yes, sir.
Okay. Can I proceed? Can I rub it? Have you all completed?
Yes, sir.
Okay. So Hess's law is a very, very important phenomenon, or you can say law, which is provided to further prove that delta H is a state function. And what is a state function? State function are those functions which depend only upon initial and final states, but not upon the path taken. So thereafter, we'll move on to the next topic, right? Bond enthalpy. Bond enthalpy. Okay. Now, before you write down the notes based on bond enthalpy, its definitions, we need to simply understand that if someone asks you that what exactly is a chemical reaction, okay, chemical reaction mane ki. So we can say that chemical reaction is nothing but it involves bond breaking and bond formation. Suppose we have a chemical reaction A2 gas plus B2 gas gives twice of AB gas. So this can be written as A bond A plus B bond B gives twice of A bond B, isn't it?
Yes, sir.
So until and unless you break down the older bonds, will it be possible to form new bonds?
No, sir.
No, sir.
No. So you need to break down older bonds, then only you can think of forming the new bonds, because during any chemical reactions, no new atoms are created or no older atoms are destroyed. It is just involving the rearrangement. The atoms are rearranging their positions. And that is why we say that in order to break down the older bonds, energy needs to be supplied. Okay, so you have to supply energy, because to break something, we need to supply energy. And when new bonds are formed, energy will be released. So what is the sum total of the energy required and energy released? That will be called the bond enthalpy. So accordingly, it has been calculated that in terms of bond enthalpy, the enthalpy of reaction will be summation of delta H of bond breaking. That means how much energy is required to break the bond, minus summation of delta H of bond formation. So all these energies when put, that is going to give us the idea whether the net resultant will be negative or positive. See, if the summation of these two or subtraction of these two comes out to be a positive value, can we say that energy is required in breaking the bond is more than that of energy released when bonds are formed? If this is greater than this, then only delta H will be greater than 0 or not?
Yes, sir.
And if delta H is greater than 0, it means it's an endothermic process. That means the net energy will be absorbed, isn't it?
Yes, sir.
Awesome.
So why certain reactions are endothermic, whereas some reactions are exothermic, can be understood on the basis of this criteria. If the total energy is required is more than that of total energy released, then the net energy will be absorbed and the process will be endothermic. On the contrary, if total energy released is greater than that of energy required, then the net resultant will be what? Exothermic or not?
Yes,
Awesome.
sir.
So this particular values, after we put them in, so depending upon whether this is greater than this or this is greater than this, accordingly positive and negative values will come. If it comes out to be positive, we call the process to be endothermic, and if it comes out to be negative, it is called exothermic. So what are the bonds that need to be broken down? A bond A needs to be broken down. B bond B needs to be broken down. So these are the bonds which need to be broken down. And what are the bonds that will be formed? Twice of delta H of A bond B will be formed. So these values, individual values of the bonds will be provided to you. We need to simply put them in and get the answer. Understood?
Yes, sir.
Awesome.
Is it clear to everyone?
Yes, sir.
Okay. Now you can write down what exactly is bond enthalpy. And one more important thing, let me explain to you first. See, if a molecule is diatomic, that means it consists of only two atoms in it. Then to break 1 mole of such bond, whatever energy is required is also called bond dissociation enthalpy. Bond dissociation enthalpy. Or bond enthalpy. Bond dissociation enthalpy or bond enthalpy. For diatomic molecule, which comprises of only one type of bond, if you take 1 mole of such bond, then whatever energy needs to be provided so as to break this into the constituent atoms will be called bond dissociation enthalpy, or also called bond enthalpy. But If you come across polyatomic molecules in which the central atom is associated with same type of atoms, but more than one bond is present, then don't think that all of them are A bond B, so all will be requiring the same amount of energy, because when you are breaking this, you will be breaking in presence of the other three. When you will be breaking this, you will be breaking in presence of other two, because this has already gone off. So every bond has a separate bond dissociation enthalpy. Let us say that the bond dissociation enthalpies of each and every bond is A, B, C, and D. So in such case, bond enthalpy will not be same as that of bond dissociation enthalpy. Rather, it will be average of all the bond dissociation enthalpies. Previously also, the bond enthalpy is average of bond dissociation enthalpy, but because it's a single value, the average of a single value is the value itself, isn't it?
Yes, sir.
So hence, when we come across polyatomic molecules with same type of atoms surrounding the central atom, the bond dissociation enthalpies will be different for each and every bond, and bond enthalpy will be calculated as taking the average of all the bond dissociation enthalpies. I hope it is clear to everyone.
Sir.
Yes, sir.
Okay. So let us now try to write down what we have discussed so far. In chemical reactions, there is simultaneous formation. First, it's not formation, simultaneous breaking and formation of bonds. In bond breaking, energy is required and in bond making, energy is released. Thus, enthalpy change is related to the types of the bonds formed or broken. Thus, enthalpy change is related to the types of the bonds formed or broken. In general, bond is defined in following two terms. In general, bond is defined in following two terms. Number one, in terms of bond dissociation enthalpy, which is meant for diatomic molecules. Better you write diatomic molecules. And number two, in terms of mean bond enthalpy. Mean mane average. So this is for polyatomic molecules. So write this much, and after completing, tell me so that we can proceed further.
Sir, are you getting our voice?
Yes.
Okay, sir.
Are you getting my voice?
Sir, like
Yes,
don't know
sir.
about others, but like at times the video is a bit slow.
Is it? Is the video slow for everyone?
Sir, no, it's okay for us.
Okay. So maybe individual network problems we have.
Yes, sir.
Okay, write this much. Then we'll proceed further in understanding what is bond dissociation enthalpy.
Sir, written.
Done, everyone?
Yes, sir.
Number A, bond dissociation enthalpy. The enthalpy change accompanying the breaking off one mole of a covalent bond of gaseous covalent compound to give products in gaseous form is called bond dissociation enthalpy. So you will understand it better when we try to write down the equations. Suppose there is H2 gas. When I supply energy to it in the form of bond dissociation enthalpy, so it needs to be converted to its gaseous atomic form. So delta H say is calculated to be 435 kilojoules per mole. They all are endothermic because energy is required to break the bond. Similarly, if it is chlorine gas, so it comes out to be 242 kilojoules per mole. So whenever you are asked to form the equation on bond dissociation enthalpy, you need to convert the gaseous molecule into its constituent atoms in gaseous phase. So last class also we came across a term called enthalpy of atomization, if you remember, where the molecule was getting converted to the gaseous atoms, which means that enthalpy of atomization and bond dissociation enthalpy are same as far as the diatomic molecules are concerned. For diatomic gaseous molecules, enthalpy of dissociation, bond dissociation enthalpy is same as enthalpy of atomization. So bond dissociation enthalpy is meant for diatomic molecules, but for polyatomic molecules, as I said, which contains more than one atoms in it, so in order to calculate the mean bond enthalpy, we need to take the average of all the different bond dissociation enthalpies.
Sir,
Hmm.
sir, in the second line, did you miss out any word after covalent?
The enthalpy change accompanying the breaking of 1 mole of a covalent bond. 1 mole of a covalent bond of
Okay, sir.
gaseous
Thank you.
covalent compound. Okay, done? Can I proceed?
Yes, sir.
So whatever we have written so far is meant for diatomic molecules. Number B, mean bond enthalpy. Mean bond enthalpy. In case of polyatomic molecules, all the bonds between similar atoms are identical in bond length. However, they differ in their bond strengths. In such cases, the mean or average of bond dissociation enthalpies is considered. Suppose we have methane, and at first I break it down to give CH3 gas plus H gas. That means we have broken down only one of the carbon hydrogen bonds. Say bond dissociation enthalpy for this step requires 427 kilojoules. Again, from CH3 gas, I take out one more hydrogen. So step by step, we are breaking down the carbon hydrogen bonds. Total of 4 carbon hydrogen bonds were there, but one after another, we are breaking it down. So it comes out to be 439 kilojoules. CH2 further broken down will give you CH plus H. The bond dissociation enthalpy, say, comes out to be 452 kilojoules. And finally, the CH is going to break down to give C gas plus H gas. The dissociation enthalpy is 347 kilojoules. So for every carbon hydrogen bond, the energy is required, as you can see, according to the values provided, is nothing but different. And hence, if it is asked that what is the delta H of C bond H then? So we need to consider everyone's value and we take the average as 427 plus 439 plus 452 plus 347 whole divided by 4. And this value comes out to be 416, which is the average of all the different carbon hydrogen bonds. Understood? For diatomic molecule, there was no problem because you need not calculate the average as there is only one type of bond. So bond enthalpy and bond dissociation enthalpy will be same. But here, the mean bond enthalpy is to be considered because every bond requires different amount of energy, because when you are breaking them, they are in different conditions. So in spite of the fact that what you are breaking down is every time same, it is carbon hydrogen bond. but in different conditions. And that is why the values differ. ठीक है? हो गया? Can I proceed?
Yes, sir.
All of you have written? So after discussion of what is bond dissociation enthalpy and what is mean bond enthalpy, now we are going to correlate the bond enthalpy with the enthalpy of reaction. Relation between bond enthalpy and enthalpy of reaction. So it is like saying that suppose India, which comprises of so many different states. Now, in a particular financial year, some states may undergo loss in overall business they do. Some states are in profit. But when we talk about India as a whole, so we have to add all the profits and losses, and the net resultant will be the profit or loss of the nation. So similarly, during a chemical reaction, which comprises of bond breaking and bond making, so obviously the net resultant will be the enthalpy of reaction. So enthalpy of reaction will be summation of delta H of bond breaking. First, how much energy is required to break older bonds minus summation of delta H of bond formation. This we have already discussed. So delta RH বা delta degree RH, okay, standard যদি হয় degree বহাই দিলে হল. Say for example, for combustion of methane, you all are familiar with now what is combustion of methane. CH4 gas plus oxygen gas gives carbon dioxide gas plus water liquid. And as I said, don't forget to balance the equation. So it will be twice of water. You won't be able to say in details what will be the exact bond breaking and bond formation expression until unless you open up the structure. So methane is CH4, oxygen is O double bond O, carbon dioxide is O double bond C double bond O, and water of course is this. So we have opened up each and every structure so as to understand that which bonds need to be broken down and which bonds will be formed. So enthalpy of reaction will be how many carbon hydrogen bonds are to be broken down?
4.
4. So we write 4 of delta H C bond H, 2 of delta H O bond O, isn't it?
Yes,
Oh,
sir.
sir.
Minus how many carbon double bond oxygen needs to be broken down? This
2.
is one carbon oxygen, this is another carbon oxygen. So can we write This.
Yes, sir.
How many oxygen hydrogen bonds need to be broken down?
2.
So it's 4, isn't it? Because per molecule it is 2. So there are 2 molecules, it will be 4. Am I clear?
Awesome.
Per water, there are 2 OH bonds, but there are 2 moles. So will it not be 4 OH bonds?
Awesome.
So these values will be provided to you in the question. You simply need to put them in and get the enthalpy of reaction. Clear?
Yes, sir.
Write it down up to this much, and I'll give you a numerical to solve on the basis of this concept. Oh yeah, can I proceed?
Yes, sir.
Okay. Calculate the enthalpy of a reaction for the following. C2H2, 5/2O2, twice CO2, H2O. H2 is in the gaseous state. Given delta H C bond H equal to 414, all are in kilojoules per mole. Delta H C triple bond C 814, delta H O double bond O 499, delta H C double bond O 724, delta H O bond H 640. Okay, so at first we need to write down this expression. So HC triple bond CH, this is ethyne, plus 5/2 O double bond O gives okay. So this much I have done the help. Now you try to calculate the enthalpy of reaction by putting in all the expressions. How many carbon hydrogen bonds need to be broken down? Tell me. 2 na. This is
Yes,
carbon
sir.
hydrogen, this is carbon hydrogen, plus 1 carbon triple bond carbon needs to be broken down, plus 5 by 2 O double bond O needs to be broken down.
Sir, 5 by 2 can be taken.
Whatever moles, exactly you have to take it.
Okay, sir.
Minus 4 of delta H C double bond O, twice of delta H O bond H. Whatever be the number of moles in front, you have to take exactly that. Now you put in the values and tell me how much you are getting. Do the calculation.
Sir,
How much you are getting?
sir, minus 1286.5.
Minus 128. No, it's not coming. Anyone getting the answer? Trisha, how much you are getting?
Sir,
Subhayu, are you
ডাঙৰ
getting the
number
same?
হৈছে
Huh?
ডাঙৰ হৈ গৈছে
Kora?
No, sir, I'm doing once again.
Okay. See whether the values I have provided are same as that of what is written in the book or not. 2 into 414, is it okay?
Yes, sir.
Plus 814 plus 5 by 2 499. ठीक है?
हाँ, sir.
Minus 4 into 724 plus 2 into 640.
Yes, sir.
So how much is this? Okay. There is a mistake. There is a mistake in the book itself. You make it 460. That is why the answer is not coming. Make it 460 because in the question they have given 640. In the solution they have used 460. This you make it 460. Now you check it. What is the answer coming up? Is it coming out to be 2885.5 minus 3816?
Yes, sir.
Yes, sir.
And what is the net resultant coming out?
Minus 926.5.
Yes, sir.
Minus
Minus 926.5.
minus 926.5. What others are getting? Tell me.
Sir, minus 930.5.
In the book, it has been given to be minus 930.5. So 3816 minus 2885.5 we have to do, I think. Eleven minus 8 is 3. This will be 9. I think it's minus 930.5, isn't it?
Oh, sir.
Have you understood how to do such kind of questions?
Yes, sir.
I hope it is clear to everyone.
Oh, sir.
Hess's law and the questions on bond enthalpies are important. So you should be capable of doing. I just given one example, but you need to carry out more questions because questions may not be same. The values will be changed, equation will be changed. But if the basics are clear, then you can easily carry out. Okay?
Okay, sir.
Oh, sir.
Okay. So next day we'll continue further with another important topic called lattice enthalpy and Born-Haber cycle. So what is lattice enthalpy? Today we have mainly discussed about covalent compounds. When we talk about lattice enthalpy, so we'll be focusing on ionic compounds because whenever terms like lattice enthalpy comes in, so ionic bond or ionic compound should come to our mind. Okay, thank you. Good night.
Thank you, sir.
Thank you, sir.